Then we next we next, looked at the Gauss law, and we saw that the Gauss's law states that the closed surface integral d bar dot ds bar is equal to rho v. Was the Gauss's law. And then we also, try to represent the Gauss's law in differential form. So we represented in integral form as well as in differential form. So this is the integral form of the Gauss's law, and this is the differential form of the Gauss's law. Now, I think this is the problem where we stop. So now we are now trying to apply the Gauss's law to find the electric field. And as I have told in the previous class, Gauss's law becomes very handy and you will get the answer very quickly when your problem has symmetry. And I have explained it to you, what does symmetry means in this case, that your electric field is a function of only R in spherical coordinates, or a function of rho in cylindrical coordinates, or a function of only X or only Y or only Z in the Cartesian coordinates. Then it becomes very easy and very fast to obtain the electric field expression. So now here we have already, done for the point charge using the Coulomb's law. Now we are doing it for the point charge again, but using the Gauss's law. So what does the Gauss's law says? We are going to use this expression, which is the closed surface integral of d bar dot ds bar is equal to the charge enclosed. That is, the closed surface integral of my electric flux density is equal to the charge which is enclosed in that closed surface. So now here you have the point charge, so which is placed at origin. So it is placed at origin. And now we need to find the electric field of this point charge. So whenever you need to apply Gauss's law, you have to first enclose your source, whether it is a point charge, whether it is a line charge, whether it is a sheet of charge. You try to enclose it in a closed surface, and you can take any shape of the closed surface, and that surface is called as Gauss's surface. And then we apply the Gauss's law on that Gauss's surface. So if it is a point charge, we have a little bit of experience that the point charge, the electric field will be radial. So it's better to enclose it in a spherical shell. So this is my spherical shell. Spherical shell. So it's a closed surface. Okay, it's a closed surface, the spherical shell. So something like this. So this is my point. So this is my charge Q. And this is my spherical shell. Okay. Now what we are doing, we are applying the Gauss's law. So the closed surface integral d bar dot ds bar is equal to the charge enclosed. Now we need to find d bar dot ds bar, right? So we need to find the electric flux density dot product with the ds. Now we have seen that this is a spherical shell, right? So this is a spherical shell. Now what is the unit normal to this spherical shell?
It's the flux.
Yeah, it's the flux, but I want to find the unit normal for this vector ds. So the unit normal for this vector ds will be, if you remember in our last class, I explained about the open surface and the closed surface. So for the open surface, the unit normal can be outwards or it can be inwards. But for a closed surface, the unit normal will always be outwards. So the unit normal for this one will always be pointing outwards. So something like this. It will always be pointing outwards. So this will be my unit normal, or this will be my unit normal. You can put it anywhere. See, this is a 2D figure, guys, but you can think that this is nothing but your unit normal, which is coming from your soccer ball. So you have your soccer ball and the unit normal. So this is your soccer ball. Just remove this. So you have a soccer ball. So this is like a soccer ball. So the unit normal is coming from here. The unit normal is coming from here. The unit normal is coming from here. So this is the unit normal. And what will be the unit normal? So what will be this normal? This will be your AR, correct? Because it is radial. So it will be AR. Now, so if we now continue with our analysis, so this becomes your AR. So this becomes your AR. So this AR will be the unit normal of my DS vector. So for my DS vector, it will be some value, DS value times AR. Clear? So if you want to take that small elemental surface of your sphere, so you can take that elemental surface here, and that elemental surface value will be here, elemental surface area times AR. Now let's visualize what is d bar, electric flux density. So now for the point charge, we know for the point charge, the electric flux density will, since d is equal to epsilon E, so the electric flux density follows the similar direction as your electric field. So for a point charge, the electric field will be radial and it will be going outwards because my charge Q1 is positive. So these big lines which I'm showing you, this is the direction of the electric field. See, this is the direction of the electric field. So now in this problem, I know a little bit information about the electric field. So for a point charge, I know that for the point charge, the electric field will be radial, but I don't know what will be its value. And therefore, Gauss's law helps in finding that value very quickly. But some information about the electric field direction should be known to you in order to apply Gauss's law in an efficient manner. So this is your electric field, d bar. Now, if you see, the electric field d bar will also be some magnitude. And what is the direction? Its direction is also AR, right? Radial. Its direction is also AR. So in a way, this is satisfying. That is, your ds bar vector is becoming parallel to your unknown electric flux density vector, because we know its direction. So therefore, based on this direction, we are concluding this one. Your ds bar is same as d bar. So this is my ds, and this is my ds bar, and this is my electric flux density d bar, unknown one. And see, they are parallel. They are parallel. So in a way, the dot product of these two, I can simply replace by the multiplication, and I can remove the vectors, because it will be AR dot AR will become 1. So therefore, it will be essentially This part which is unknown, so that I am naming it as D. And this part which is your elemental surface value ds, I'm naming it as ds. So therefore, this dot product with this will simply become d multiplied by x and is equal to the charge enclosed. What is the charge enclosed? Q1. So Q1 is the charge enclosed. So closed surface integral, this d bar dot ds bar is equal to charge enclosed has been simplified to a scalar. So here you have a scalar now. You do not have a vector. So that makes application of Gauss law very efficient only under symmetries. So here, as I told you, symmetry, your electric field should be a function of either only r for spherical coordinates or rho for cylindrical coordinates or x or y or z for rectangular coordinates. Then it becomes very efficient and you will get the answer very fast. But having said that, it doesn't mean you cannot apply Gauss law where you don't have a symmetry. You can apply, but what will happen is applying Gauss law and applying Coulomb's law will take the same time. It will take the same time. So you can apply any one of them. But if you have a symmetry, then rather than apply Coulomb's law, if you apply Gauss's law, you will get the answer very fast, as you can see here. So the vector has changed to scalar. Now just evaluate this. So in this, our unknown is this one, right? This is our unknown, which is the magnitude, this one. So now find this one. So this is our unknown. So this unknown is taken outside the surface integral. So d surface integral ds is equal to q1. So this d can be taken outside the surface integral because if this d, if it has a if it is in the radial direction, then it will not have any, say, it will not be a function of r. It will not be a function of r. So this is again coming from our chapter 2 and chapter 3. So if I take d outside, surface integral of ds is equal to q1. Now what is the surface area of your spherical shell? The surface area of my spherical shell is nothing but 4 pi r square. So integral of ds is nothing but simply 4 pi r square, and therefore my d is equal to q1 over 4 pi r square. So this is the magnitude. And now if I substitute here, my d bar will be what? Q over 4 pi r square times AR. This is my D. And therefore, E will be, we know, D bar is what? Epsilon E bar. So E bar will be D bar divided by epsilon. So E bar will be D bar divided by epsilon. So epsilon will appear in the denominator. So epsilon is here. So E is Q1 over 4 pi epsilon r square. This is the magnitude, or for the vector, it is Q1 over 4 pi epsilon r square A. So this is the expression for a point charge placed at origin. And we have seen the same expression when we used Coulomb's law. When we used Coulomb's. So what is happening? We are using, see, we used Gauss's law, and from that Gauss's law, we derived Coulomb's law. So if from the Gauss's law, if we derived Coulomb's law, then Coulomb's law is no longer the fundamental law. We use the word fundamental laws for those laws which cannot be derived from any other law. Then they are called as fundamental laws. So here, since we were able to derive the Coulomb's law using Gauss's law, therefore Coulomb's law is no longer a fundamental law. And therefore Gauss's law is the fundamental law. So this is how you can apply Gauss's law for finding the electric field. And this is how you do it. And again, as I told you, how you take D outside, because D will no longer be a function of R, because the D is uniform over the surface. So the D is uniform over the surface. That means it will not be a function of R. That's why you are able to take it out. So the good thing is when the symmetry falls, sorry, when the symmetry is in place, all these things will, come together. It will become parallel. D and ds bar will become parallel, and D will become uniform over the surface, over the Gauss's surface, and therefore you can take D outside. So both of these comes together when this symmetry is in place. And at that time, the Gauss's law becomes very easy. Okay. So let's take this example also. This is for a line charge. We already derived for a line charge, right? So let's now derive it using the Gauss's law. So again, it's an infinite line. It's a straight line. And it has uniform line charge density, rho L. Now, how are we going to apply Gauss's law? As I told you, first we need to enclose it in a closed surface. So now what could be the best closed surface, or what could be the coordinate system that you need to, you want to use in order to apply Gauss's law? This you have to decide. And again, this comes from a little bit of information that you know about how would be the direction of the electric field of this particular source of charge. So for line charge. Now from our say knowledge, we know that it's a line charge. It has a positive charge density. So therefore the electric field should be going outwards. So it will be going outwards like this. And now we don't know the magnitude of that. So let's find that magnitude. And that magnitude, Gauss's law can allow us to do it in no time. Now, what could be the best Gauss's surface? Because now it's a line and the field will be in this manner going away. So the best one would be the cylindrical coordinates. So you can select the cylindrical coordinates here. Now, once you select the cylindrical coordinates, what could be the best Gauss's surface in cylindrical coordinates? The best Gauss's surface is your cylinder. So this is a closed cylinder. It's a closed cylinder. So you have a okay. So you have a closed cylinder. So you have this line. So this is infinite. So I'm placing it on the z-axis, and therefore this will be my rho axis. And now the Gauss's surface is my cylinder. So I'm enclosing it in a cylinder. Now you can think about it. So this is a closed cylinder. So how many sides does this closed cylinder have? Just visualize.
3.
3. The top, right? It is closed. It's not open. The bottom, this is also closed. And this sides. So this is also closed. Now the thing is, you are enclosing the charge, line charge, inside a closed cylinder. But you need to have a finite size or finite length of the cylinder. You cannot put the cylinder of infinite length to apply Gauss's law. It should be of finite length because my line charge is of infinite length. See, it's of infinite length. It is going like this and like this. But unfortunately, you cannot enclose it in an infinite closed cylinder. So you have to enclose it in a finite length. And therefore, you have to say that, okay, this is finite length and this length is L. Okay, this length is L. And its radius is R. Because in the previous case, our spherical shell radius was R, and that's why we applied Gauss's law on that spherical shell, and therefore the area of the spherical shell became 4 pi r square. Here the the radius here is rho. So this is our Gauss's surface. Now again, from our knowledge, so the knowledge is telling us that the electric field will be electric field will be going away. So this is something you will see in the electric field going away, right? So therefore your electric field will be your d bar, or electric flux density d bar will be your d times a rho, correct? It will be d times a rho because this is the rho direction. This one, this is the rho direction. So it is d times a rho. So let me write it properly. So your d bar will be equal to d times a rho. Now closed surface. So now we need to now evaluate this d bar over the closed surface. So how many surfaces we have? The top surface, the side surface, and the bottom surface. Okay. Now, what will be the unit normal for this top surface when you evaluate the surface integral? Yes, what will be the unit normal? Can anybody tell me?
It will be indicating upwards.
Yes, it will be going upwards because it's a closed surface. So therefore the unit normal will always point outwards. So if I am considering this surface, the unit normal will be this one, right? Which will be AZ. Now for surface number 3, what will be the unit normal?
Downward.
Minus AZ.
Going downward. So it will be minus AZ. And for this surface, surface number 2, it will be your A rho. Correct? It will be your, the unit normal will be your A rho for this side area. So it will be A rho. So this, so if you want to integrate over this area, the unit normal is AZ. So here I will get ds bar is equal to ds times AZ for surface 1. For surface 3, I will get area ds bar is equal to ds times minus AZ. So therefore the minus, let me write it here. So it will be minus AZ. And for this one, your ds bar is equal to ds times a rho. Correct, got it? So we got all the three. Now you tell me, if I want to do this integration of this d bar, if I want to do this integration of this d bar over this surface, it will be, because it will be integral of d bar dot ds bar, dot product of d bar with ds bar. So what will be the result of integration, surface integration for this area? See here, it is a rho, here it is az. So d bar dot ds bar is nothing but a rho dot product with az. And what it will be? Yes, a rho dot
0.
0.
0. It will be 0. So therefore, the contribution of this top surface towards d bar dot ds bar is 0, because it is az dot product, sorry, a rho dot product with az. So it is 0. What about the bottom? Same.
Also 0.
A rho dot product with minus az, but it doesn't matter. A rho dot az will give again 0. So the contributions from the top surface and the bottom surface is 0. So the only surface that contributes is this surface, because here your d bar dot ds bar is a rho dot a rho. See, a rho dot a rho. So only you will get the contribution from this side. And this is what
Doctor, can you
are
repeat
doing
that
here.
point?
See here, so it is closed surface integral d bar dot ds bar is equal to the charge enclosed. So this closed surface integral is made up of three surfaces: the top, the side, and the bottom. 1, 2, and 3. So that's why I am saying that integral over 1 plus integral over 2 plus integral over 3 is equal to, what will be the Q now? What will be the charge enclosed in the cylinder? It's an infinite line. It is carrying a uniform charge density rho L. So can we find the charge which is enclosed in the cylinder? What will be the length of this line enclosed in the cylinder?
H.
The length of the line will be h. And if you multiply this length of the line, which is h, with the charge density rho L, I will get the charge enclosed in the cylinder. So it is simply rho L multiplied by the length of the line which is enclosed in the cylinder, that is h. So it is rho L multiplied by h. This will give me the charge enclosed. Yes, Taha.
Can you repeat why the top and bottom surface are 0?
Okay. So what I am saying is, so let me use the annotation here. So now my closed surface, Taha, is this top surface, which is circular in nature because it's a closed surface. The bottom surface, which is circular in nature, right? And then this sides. Correct? This is another area. So you have these three areas. Yes, Taha?
Yes.
You have these three areas, correct? Now, from our experience, what we know, from our experience, we know that my electric field for this infinite line should go outwards. That means my electric field or the electric flux density is only a function of arrow, because it will go in this manner. Right? So, and this direction is the rho direction. So that's why it's a function of only arrow. Correct? Now, when we want to do surface integrations, we need to find the surface normal. So if you want to find the surface integration of this one, then the surface normal. if you take this small surface here to integrate this circle, then this is the normal that you will consider. And this normal is nothing but your AC. So therefore, in this case, sorry. So therefore, in this case, your DS1, which is the first surface, will be your DS1 bar is equal to your DS1 magnitude times AC for this surface. Clear?
Yes.
Yeah. Now for the bottom surface, again, it's a part of a closed surface. So the unit normal should always point outwards. So therefore, for this bottom surface also, the unit normal should point outwards. So if I take a small elemental surface to find the surface area of this number 3, this will be the unit normal. It should be pointing outwards. And this is minus AZ dash. So therefore, in this case, my DS3 unit vector will be equal to the elemental surface value DS3. And what will be its unit vector? Its unit vector will be minus AC. So this will be equal to minus DS3 AC. And for the third surface, this is this surface. So this is like a sides, this is the sides of a cylinder, right? So if I find a small surface of this one, elemental surface, for the side of a cylinder, so the unit normal will be coming out like this. And this unit normal is nothing but a rho. So therefore, so for this case, your DS2 will be equal to your DS2 value times A. So right now, I'm not evaluating what is this DS2, what is this DS1, and what is this DS3. Why? Because I will evaluate only for that which stays. And why should I evaluate for those which is becoming 0? It's unnecessary waste of time. Now, what will happen? If I apply closed surface integral of d bar dot ds bar is equal to the charge enclosed, I will get this one, which is integral over 1 d bar dot ds1 bar plus integral over 2 d bar dot ds2 bar plus integral over 3 d bar dot ds3 bar. Now from these three, tell me which one will become 0. So d bar dot ds1 bar is d bar ds1 bar dot product. So a rho dot product with az will become 0 because a rho dot a rho will become 1, whereas a rho dot product with az will become 0. So therefore, this will go to 0. Then d bar dot product with ds3. See here, d bar dot product with ds3 bar. So it will be a rho dot product with again az. With again this goes to 0. So therefore, only this one will be left, which we want to evaluate. Okay, so only this one will be left. So you will get only integral over 2. This will be just d times ds2. Correct? Because d bar dot ds2, so d bar is a rho, d rho a rho, and ds2 is ds2 a rho. So this will be d rho times ds2. So this is the answer. I think now it is clear. Correct?
Yes, thank you. Thank you.
Okay. So now if we go further, it's just the simple integration. So we are going to get the answer only for our second surface, which is our triangle, which is our side of the cylinder. And then you find the integration of that. And again, the same concept applies, because my magnetic, sorry, not magnetic. So again, so only this will survive, and this is rho L over H. And again, the same thing applies, because my magnetic flux density I'm evaluating over the side of the cylinder, and it is uniform over the side of a cylinder. So therefore, it will not be a function of rho. And that's why I can take D outside. So therefore, your ds, integral over of 2 ds, is nothing but the area of this cylinder, because it's the side. So area of the side of the cylinder, not the closed, open cylinder. Area of an open cylinder is nothing but 2 pi rho h, because rho is the radius, h is the height. So it is 2 pi rho h is equal to the charge enclosed is rho L times h. Therefore, the magnitude of my electric field, electric flux density is rho L over 2 pi rho, or the magnitude of my electric field is rho L over 2 pi epsilon rho, because D is epsilon E, and therefore the electric field is rho L over 2 pi epsilon rho times A. And again, this is what we derived before using Coulomb's law. So therefore, again, from the Gauss law, we are deriving the Coulomb's law. So therefore, Gauss law is the fundamental. So we took two examples where we applied Gauss's law, and we found for the point charge, we found for the line charge. Now, this is for the infinite sheet. Okay. So this is an example for the infinite sheet. So you have an infinite sheet, and here for the infinite sheet, because it's a sheet, it's better to think in the rectangular coordinates, and therefore the closed Gauss surface, the best closed Gauss surface in our rectangular coordinates is a cuboid. So you are considering a small cuboid, and you are considering this cuboid such that half of the cuboid is above the sheet and half of the cuboid is below the sheet. Why? Because we want to include some charge inside this cuboid, because my cuboid is my closed surface. The cuboid is my closed surface. So it's a hollow cuboid. It's my closed surface. And to have the charge enclosed in the closed surface, that's why we are keeping it half up and half down, so that part of that infinite sheet, which is carrying the uniform charge density rho s, will be included in that cuboid. So guys, this one I'm leaving it to you. So I want you to go through this, in your home when you review the material. So the solution is already there. So I'm leaving it to you. But again, you will see that when you apply the Gauss's law, you will get the same expression that we have already derived using the Coulomb's law, which is E bar is rho s over 2 epsilon times Az for z greater than 0, and it is minus for z less than 0. Okay. Now let us take this example. So this is now the example of a sphere, because we did not do the derivation for the sphere using Coulomb's law, because there I asked you that you can look it into the book and see the derivation. We got the expression of the electric field due to a sphere using Coulomb's law. But now let's derive the expression for the sphere using Gauss's law. So this is my sphere. If you see here, this is my sphere. This is my sphere. And now my sphere, it has a radius of A. So let me erase this. So this is my sphere, and it is of radius A, and it's a solid sphere. Okay. it's a solid sphere, it's a radius A, and it is carrying a uniform volume charge density rho v. So it's carrying a uniform volume charge density rho v. Now, how do you find the electric field due to this sphere, which is carrying a uniform charge density rho v? What would be the best Gauss surface to enclose this sphere? Yes.
The same.
What will be the best coordinate system and what would be the best closed surface, the Gauss surface?
Spherical.
Spherical coordinate.
Yeah, so it will be the spherical coordinates, and the best Gauss surface will be a spherical shell. And inside the spherical shell, you are enclosing this sphere, and this sphere is placed at origin. And let us assume that this, our Gauss's spherical shell, has a radius of r. Okay. Now, in this case, what will be our answer? Yes, what will be our answer? Again, this is sphere, and it has a charge density of rho v, right? So now again, it's sphere, it's a positive charge, although it's not a point charge, but it's sphere. And how would its electric field will look like? Again, its electric field will be pointing outwards like this, going away. So your d bar will be a function of d times AR, radial. The field will be radial. Okay, so this is the information that I got. Now we need to find what is this unknown d. So therefore, let's apply the closed surface integral. So the closed surface integral, if we apply, okay, so if we apply the closed surface integral, and here I have put my Gauss's law on this outside, right? So this, we say it as a case where this r is greater than a. That means I have applied the Gauss's surface outside the sphere. So that's why this is r is greater than a. And this is my spherical surface S2. This is my spherical surface S2. Now let's apply Gauss's law here. So what you will get? Closed surface integral of S2, which is this spherical shell S2, d bar dot ds bar is equal to the charge enclosed, right? Now again, this is d bar is d times AR bar. Now what will be the unit normal of the spherical shell? We have already done for the point charge, is the same. So the unit normal for the spherical shell, closed spherical shell, when you want to find the closed surface integral, so this closed surface unit normal will also be pointing in AR. So therefore, its ds2 bar will be equal to your ds times AR. And that's why if you do the d bar dot, okay, so they are using it is using ds. Okay, so d bar dot ds bar, so dot product d bar and ds bar, so it will become integral. Yes, what it will become? It will become integral of d multiplied by ds is equal to the charge enclosed. Correct? Because this d and d bar, they are parallel. So this is your d and this is your d bar. They are parallel because AR dot AR will again become 1. So it will be simply integration of this d, which is unknown, multiplied by ds is equal to the charge enclosed. And again, you can take d outside And then integral of this surface area, the spherical shell surface area, will be 4 pi r square, because we assumed r as the radius of my this surface, closed Gauss surface S2. Charge enclosed. So what will be the charge enclosed inside this Gauss law? The charge enclosed is nothing but the total charge Q which your sphere is carrying. And what will be the total charge Q that your sphere will be carrying?
Volume times the density.
Yeah, so it's the volume charge density multiplied by the volume of your sphere. And the volume of your sphere is 4 by 3 pi a cube, because a is the radius. And therefore, if you just say do the simplification, I will get d bar as rho v a cube by 3 r square ar. And it is same as what we have seen in our notes, or you can go and check it in the book. What will be, this will be the electric flux density or the electric field. You will have an epsilon here for a sphere. So this is for r is greater than a. How about the case where r is less than a? Okay, how about the case where r is less than a? Because your sphere is of now finite volume. So if this is my sphere, and this is the origin, and this is A, we found what is outside, which is this expression. This is the electric field. But what about inside? So if I put a small Gauss surface here and apply the Gauss's law on this Gauss surface, what will be the electric field that you see inside the sphere? This is what now we are trying to evaluate. So I'm taking this as R, and I'm taking this as the surface S1. And again, the idea is the same. This will be the unit normal. So this unit normal ds will be equal to ds AR. And again, how would be the electric field which is coming out from this surface? Again, it will be d bar is d times a rho, AR. So again, the dot product of this will become simply d multiplied by ds. Just give me a minute, guys. I'm finishing it. See, again, it will be the same thing. See, d integral of ds, and again, it will be d times 4 pi r square. 4 pi r square, but here my r is less than a. Now, what will be the charge enclosed here? This is the only thing that we need to find. What will be the charge enclosed here? Because this is the only charge which is enclosed in our Gauss's surface, not the whole sphere, only this much. And how you can find? Volume charge density multiplied by only volume of this part. And what is the volume of this part? It is 4 by 3 pi r cube. That is only this much of volume, not the whole volume, only this much of volume. So 4 by 3 pi r cube. It will not be pi a cube, it will be pi r cube, because only this much is the volume, only this much is the part of the volume of your sphere which is enclosed in this closed surface S1. So therefore it will be pi r. So therefore, when you simplify it, you get d bar is rho v r over 3 times a. And therefore, you will see that whether you are inside the sphere or whether you're outside the sphere, your electric field is radial. The only thing is the magnitude changes. So inside the sphere, the magnitude is linear, the increasing. And once you are outside the sphere, it is decreasing as a function of r square. Okay. So we will stop here. And next week, we are going to have the quiz, and it will be on Thursday. I'm going to send the announcement to you. Okay. Thank you very much, guys.
Okay. Doctor.
Yes.
Just I had a problem in the beginning. At 5, the system let me out, and I had to join again. But just I want to know.
So when did you log in, Ibra?
No, I log in at the beginning, 10.
Okay.
Just after maybe around 6 minutes, he let me out, and then I rejoin in 6 minutes. just 1 minute let me out. I don't
Okay,
know.
okay, 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 no problem. Thank you.
Okay, thank you so much, Doctor.
Thank you.